It's Paul Bamberg with the third introductory video for Math 117. This one you should watch before the class on Thursday, September 8th. And the topic is sets and sigma fields. We're getting away from horse racing for a while and getting back into pure mathematics. First, let's talk about infinite sets, and more specifically, about countably infinite sets. What makes a set countably infinite is that there exists a one-to-one correspondence, bijection is a good synonym for that, between that set and the natural numbers. And for the natural numbers, you can start either with 0 or with 1. So when you name the elements of the set, you might want to name the first one A0, or you might want to name it A1. Then you go on to A2, A3, A4. And the point is, there is no largest number used. You go all the way to infinity. Notice that any time you use this notation A sub I for the elements of a set, you're implying that this is a countable set. And this is a common rookie mistake made by undergraduate mathematicians. When asked to prove something for an arbitrary set, you mustn't specify the elements of the set as A sub I, because that's implying that it's countably infinite. Countably infinite sets have a lot of useful properties. We'll prove some of these later, but for the moment I'm just going to state them. First, any subset of a countable set is also countable. So, for example, the prime numbers being a subset of the positive integers are a countable set. If you intersect a countable set with any other set, you create a subset, and therefore such an intersection is also countable. A little bit more interesting, it's fairly easy to prove that if you take the Cartesian product of two countable sets, you end up with a countable set. That is, the set of pairs of natural numbers is also a countable set, and it's an easy inductive proof to extend this to the Cartesian product of n countable sets. You just say the product of n countable sets is the Cartesian product of two sets, one of which is the product of n minus 1 countable sets, and the other of which is a single countable set. Finally, and arguably this is the most useful property of all, a countable union of countable sets is also still countable. Here are some examples. I already mentioned the prime numbers. If you look at the subset of the integers that lie between 100 times e and 100 times pi, you're forming the intersection of a countable set with another set, and the result is still countable. The rational numbers are a well-known countable set, and a simple argument for this is that the set of fractions involving positive numbers, m over n, is a Cartesian product of two countable sets, and the rational numbers are a subset of this for the simple reason that you only count m over n as a rational number if the fraction m over n is in lowest terms. The principle that the Cartesian product of countable sets is countable means, for example, that the set of points in three-dimensional space where all the coordinates are rational, that is, the set of triples of rational numbers, is also a countable set. If you look at all the subsets of the positive integers that contain precisely 4 elements, that's a countable set. An easy way to show this is to say you can consider 4-element subsets where the sum of the 4 elements is 10, like the set 1, 2, 3, 4. Then you can go on to sets that total 11, sets that total 12. Each of those is a finite set, and its countable union is also a countable set. Once you know that all 4-element subsets form a countable set, the same is true, for example, for all 17-element subsets, you have a countable union of countable sets one for each size, so the collection of all finite subsets of the positive integers is still a countable set. Interestingly, remove the word finite and the conclusion is no longer true. What about uncountable sets? What makes a set uncountable is that any attempt to prove it countable by assigning serial numbers to its elements is guaranteed to fail. The best known example of a countable set consists of the real numbers between 0 and 1, and you may have seen Georg Cantor's famous proof that this set is not countable. Closely related to this uncountable set is the set that involves all infinite sequences of elements from a two-element set. In the context of this course, probably the cleanest example of this is the set of all infinite sequences of coin tosses, of which one example would be tails, heads, heads, tails, heads, heads, tails, tails, and so on forever. If you consider all subsets of the positive integers, that's an uncountable set, and that actually follows immediately from the preceding example because you can specify a set of the positive subset of the positive integers by a sequence like f, t, t going on forever, f meaning 1 is out, t meaning 2 is in, t meaning 3 is in, and so on. And more generally, if you take the collection of all subsets of any infinite set, you've got an uncountably infinite set. The usual way of proving that a set is uncountable is you assume that it's countable and then do a construction that leads to a contradiction. This famous proof is found in our textbook. It's proposition 3.1 on page 34. What about the real numbers? Well, there are at least 4 ways to characterize a real number like pi, and the first one you probably learned was a real number is an infinite decimal. Pi is 3.141592, and so on forever. This is an appealing characterization, but it has a major drawback. It's very difficult to prove that the axioms for a field hold. To prove, for example, that multiplication of real numbers is commutative and associative. A slightly cleaner example is to say a real number can be characterized as the least upper bound of an increasing sequence. Back in the 18th century, Euler discovered that if you constructed the sequence where the first element's 2, the next one is 2 times 1 plus a third, the next one is 2 times 1 plus a third times 2/5, and so on. The smallest number that is larger than anything in that sequence is pi, and the real number pi is the limit of this increasing sequence. But notice, each element of this increasing sequence is a rational number. It's just a sum of products of fractions. More generally, and this is probably the most useful characterization of a real number, take any bounded non-empty set of real numbers. The least upper bound of that set is also a real number. Finally, you can construct a real number as the intersection of so-called nested intervals. This is best illustrated by an example. It was known back in southwest India, 15th century or earlier, that pi over 4 is 1 minus a third plus a fifth minus a seventh. This was later discovered in Western Europe, and a mathematician named Gregory got his name attached to this. Multiply this by 4, you get pi is 4 minus 4 thirds plus 4 fifths, and so on. So you can say pi has to lie in between 4 minus 4 thirds and 4. Take 2 more terms, you can get another smaller interval within which pi has to lie, and you can say pi is the unique number that lies in all of these nested intervals. Now let me review the concept of sequences. First, let's think about increasing sequences. We've got an increasing sequence of real numbers, a1, a2, and so on. And let's imagine that this increasing sequence has a limit a. That limit has to be the least upper bound of the sequence. This will be the approach most commonly used in the Dineen textbook, and it has the advantage that it relies only on the fact that the real numbers are ordered, that given two real numbers, you can say either that they're equal or that one of them is unambiguously larger than the other. It never explicitly refers to the difference between two real numbers, and for that reason this approach also generalizes to other types of mathematical objects. For example, we'll be able to talk about increasing sequences of sets. However, there's a more conventional definition. You might, if you were lucky, have met this when you first studied calculus, or maybe you met it later on in a real analysis course, or maybe you've never met it, in which case you've got something new to learn for this course. What it says is, given any positive quantity epsilon, if you go far enough along in the sequence, and usually capital N refers to the number of the term that is far enough along, all terms beyond that in the sequence, all the a sub little n for little n greater than capital N, have the property that the difference between a and a sub n is less than epsilon. This is the conventional definition of limit, and it has the advantage that it works even when the sequence a sub I is neither an increasing nor a decreasing sequence. Now let's start thinking about probability. We're imagining doing some sort of experiment, and we'll use capital omega to refer to the sample space in which the outcome lies. The sample space is frequently not anything that you recognize as a standard mathematical object. The experiment might be something like flipping a coin or rolling a pair of dice. It could be a much more complicated thing like running a horse race or acquiring 100 shares of Microsoft stock and holding them for a year. An event, this is a definition, is simply a subset of the sample space. So a sample event for the coin flip is the coin comes up heads. For rolling a pair of dice, the total is 7 or 11. For the horse race, it could be something complicated like, after 4 furlongs, Dineen's Pride was ahead, but eventually Faust's Fury won with a time of 1 minute and 47 seconds, with Arbitrageur in second place 2 lengths behind. You could imagine, in fact, that you might need a function giving the position of each horse as a function of time in order to specify everything about the horse race. With the Microsoft stock, you could say a sample event is after 1 day, it's up 45 cents. After a week, it's down by $1.23. But after a year is over, it's gone up by $4.56. Again, you could imagine specifying the outcome of this experiment by a graph of the price of Microsoft stock as a function of time. In simple cases, any subset of the sample space is an event, and we can attempt to assign a probability to that. However, there are frequently only a limited number of subsets to which we want to assign probabilities, and that's one reason that we're going to have to invent the concept of a sigma field. For example, in the case of the horse race, it may be the only events we're interested in are Dineen's Pride wins, Faust's Fury wins, or Arbitrageur wins. We don't care who was in second place. We don't care what the time was after 4 furlongs or anything else. And worst of all, in some cases, if you say, oh, I'm just going to assign probabilities to all the subsets, you end up with mathematical inconsistencies. Within a couple of weeks, you will meet something called a Vitali set to which no probability can meaningfully be assigned. And that's why we need the concept of sigma fields. The set of events to which we're actually going to assign probabilities is called a sigma field. A most unfortunate term, because field is used in a way that has nothing whatever to do with gravitational field or magnetic field from physics, and nothing to do with field of rational numbers or field of complex numbers from analysis. Some people use sigma algebra, but our textbook uses sigma field, and so will I. Generally, we use a fancy typeface. This is Math117Cal in LaTeX to represent a sigma field. Now, in order to be able to formulate axioms for probability, we're going to need to impose some requirements on a sigma field. First, the entire sample space, which has to have a probability of 1, has to be in the sigma field. Second, if an event is in the sigma field, e.g., Deneen's pride wins, so is its complement, Deneen's pride loses, and that also tells us, combined with number 1, that the empty set has to be in the sigma field. Finally, if you have a countably infinite set of elements in the sigma field, the infinite union of those events also has to be in the sigma field. And the fact that you have to restrict this idea to countably infinite sets was one of the key mathematical discoveries of the 20th century. Once we have a sample space and a sigma field, we have constructed what's called a measurable space. Now, there are other properties of sigma fields. You'll encounter them, and you'll probably memorize a bunch of them. But the other ones are all theorems that we can prove. The fact, for example, that the intersection of two elements in a sigma field must also be in the sigma field is a provable theorem. I'm not going to mention them today. It's reasonable to ask, what's the smallest and largest possible sigma field? Well, the smallest one has to contain the sample space itself, omega, and its complement, the empty set. So this is a trivial sigma field, and it's going to be a subset of any other sigma field. On the other end, the largest possible sigma field consists simply of all the subsets of the sample space. The jargon for this is it is the power set of omega, and it's symbolized by 2 to the omega power. Why this notation? Well, suppose that the sample space consists of the numbers that can show up when you roll a die, 1, 2, 3, 4, 5, and 6. If you consider all subsets of the possible die rolls, you have to answer the question, do you want to include one or exclude it? Do you want to include 2 or exclude it? You have to make a binary decision for each of the 6 numbers. You have 2 to the 6th possible outcomes, and selecting one of those 2 to the 6th outcomes will give you an arbitrary subset, like the odd-numbered rolls 1, 3, and 5. So in this particular case, omega has 6 elements, and the number of elements in the power set is 2 to the 6. For a finite sample space, life is really quite simple. The power set is bigger than the sample space itself, as long as there are at least 2 elements in the sample space, but it's still finite. If your sample space is countably infinite, it will turn out that its power set is uncountably infinite, a fact which we will prove. And finally, if the sample space to start with is uncountably infinite, like the real numbers between 0 and 1, and this is a case that's going to show up as soon as we start considering things like stock prices as a function of time, 2 to the omega is worse than just uncountably infinite. This is the case that leads to great mathematical difficulties. In any event, you can say any sigma field is bigger than the trivial sigma field, and it is smaller than or equal to the power set 2 to the sample space. That concludes my introduction to sigma fields, a topic which will occupy us for a couple more classes.